Okay, so for part two here of homework 4-1, right, just have questions 9, 10, and 11 to hopefully wrap up here. So they give us a force of particle depending on the position, and notice it's not a constant, right? So they're giving us this force as a function of x, where x is in fact a quadratic, so it varies a lot. They ask what is the work done by this force as it moves from 0 to 2. Well, the biggest thing we need to realize is because the force varies, because the force is a constant, I cannot just use force times displacement. I can't just use work equals force times displacement because that only works if it's a constant force. So instead I have to take a different approach. Well, the first thing that I want you to think about, and this is going to be something we look at more and more in class as well, but right, if I was thinking work in terms of a graph, well, if it was a force versus displacement graph, then the work we know would be the area underneath the curve, right? The work would be the area under the curve. We saw that a lot last year. We will start to see it more and more this year. The reason that's important is the second you realize the work is the area underneath the curve, that tells me I should be doing integration. So, and when you see this question, probably a lot of us right away are thinking, okay, this looks similar to all those questions where I had to do the derivative or integration. And in fact, this one is one where I need to integrate the function because I'm looking for the area underneath the curve, and that's what the process of integration does for us. So I take my force equation, right? I take my function for force, which is 3x squared plus 6x. I'm simplifying it by getting rid of some of those units in there, right? And I need to integrate that. If I want to integrate it with respect to the distance, so I want to integrate it with respect to dx because that's what the area is, right? It's the integration of force with respect to x. So I'm going to integrate both sides, which would give me the work. When I integrate this side, right, I make the power bigger and then divide by the new power. So once I do that, I make this 3 and then divide by 3. So I end up with just x to the third plus, I now make this a 1 plus a 1, so a 2, and then divide by that new power of 2, so 3x squared. And then I do have my plus c that I want to make sure I don't forget. And they don't tell me the initial position or the initial force based on position, so I don't necessarily have a way of finding c. However, it doesn't matter. Because we're trying to find this, we're trying to find the amount of work done from 0 to 2 meters. So mathematically, the way that you'll represent that, and you'll see that more in calc once you get there, but we're going to go from the initial position of 0 to the final position of 2 meters. Well, when I use this bar, it's just telling me I'm going to plug in 0 and I'm going to plug in 2 meters, and I'm going to find the difference between the two. So as I do the work, as I find the integration here, I'm just plugging in again 2 for x, and I'm seeing what I get from that. And then I'm subtracting whatever I get when I plug in 0. So obviously 0 is going to be a pretty easy function to work with. What I do want you to notice here, though, is I included the plus c with both of them. So I end up with 8 plus 12 plus c minus 0 plus 0 plus c, so minus c. And the c doesn't matter, right? It cancels out. That constant term cancels out. So I end up then just with the work equals 8 plus 12, or 20 joules. So again, the big process here, I know this question probably the trickiest one on this first homework, but the big process is because I'm looking for the area, I've got to use integration. Once I do integration, yes, I do have the plus c, but when it tells me what I'm finding the c from positions, right, which positions I'm finding it from, once I plug it in, that c really doesn't make any difference. It should cancel out if I've set this up correctly. So question 10, once again, asks for work here. And if you notice, there's kind of two stages of motion, right? There's a stage where he's pushing it at a constant 60 newtons for 6.88 meters. And we know, hopefully we remember, right, that that part would be pretty easy. If it is a constant force, then I could just do force times displacement. The problem is, once he starts to tire out, and he goes from 60 to 0 newtons, obviously the force is no longer constant, which means I can't use that relationship anymore. So instead, what I would encourage you to do, very similar to what we did on the last problem, is think about it in terms of a graph. Well, if I was doing a force versus a displacement graph, then the work would simply be the area underneath the curve. So if I'm doing this graph, well, for the first 6.88 meters, I know the force is constant, right? So I'd have a constant force, no big deal, right? So for the first 6.88 meters, I would just have a constant force. Then for the next 6.88 meters, so all the way down over here, and I'll mark those in just a second, but for the remaining 6.88 meters, the force decreases linearly, and it is very important they tell me linearly because I know it's a straight line, it decreases from 60 newtons of force to 0. So it comes all the way down to the x-axis. So again, the first 6.88 meters, the force was constant, and I can pretty easily find then that area, right, by just doing force times distance, what we would normally do. So force times displacement. Then for the next 6.88 meters, which would take me to a total of 13.76, right, but again, it's just another change of 6.88, I can also find the area of this triangle, and that's why it's so important that it's a linear function, because it makes a triangle and not some type of curve there, right? So it's easier for us to calculate. So I actually don't have to worry about any type of integration or derivations or anything like that. I'm just going to say that the work equals the area under the curve, and then I just need to find the area underneath the curve. So again, there's kind of two stages here. There's a stage where we do 60 times 6.88 for the constant force, and then there's a stage where I do plus 1/2 times my 60, because it's the area of the triangle, times 6.88 again. So it's 60 times 6.88 plus another half of what that was. When we calculate that, we end up getting about 619.2. Obviously, you could round that off a little bit if you prefer, but 619.2 joules. That's how much work we've done. Again, the easiest approach, just think about it in terms of area underneath the curve. Anytime you have a force that is not constant, be thinking area and or integration. And then question 11, hopefully a pretty easy question here, just to kind of target in on kinetic energy, right? Mostly just make sure we still are comfortable working with it. So for part A, they ask us to find the change in kinetic energy, right? How much energy is needed to change its speed from 15 to 40 meters per second. Well, again, all I really need to do is find my change in kinetic energy. So my final kinetic energy minus my initial kinetic energy, right? Well, the final would just be 1/2 the mass of 1600 times the final velocity of 40 meters per second squared, so 40 squared, minus the initial of 1/2 times 1600 times just 15 meters per second squared. Right, so again, finding the initial change in kinetic energy for part A, hopefully pretty easy. It does end up being a pretty large number here. So I get about 1,100,000 joules of energy being required to increase it by that much velocity. Again, it's fairly reasonable to expect because 40 squared is large and 1600 is already a large mass as well. So nothing too out of the ordinary there. And then for part B, more of a concept question, and this is one we saw last year that I do want you to be comfortable with. Does it take more energy to increase it by the same amount of speed again, right? So going from 15 to 40 was an increase in 25 meters per second. So then I'm asking you to go from 40 to 65, which is another increase of 25 meters per second. Does it require more, less, or an equal amount of energy? And hopefully we all remember this answer. It's a very important concept, one that I do want you to be comfortable with, but hopefully we remember it, but maybe not. But it does require more. It requires a greater amount of energy. So the energy must be greater than it originally was, right? And the reason for that is just think about the fact that we're squaring this. The difference between 15 squared and 40 squared is a lot less than the difference between 40 squared and 65 squared. If you calculate these numbers, you realize that the difference here, again, way less than this difference here. So as we reach a higher and higher velocity, it always takes more and more energy to increase that velocity, right? So to bring it up 25 meters per second from 40 to 65 requires way more energy than from 15 to 40. So make sure you are kind of comfortable with that concept and comfortable supporting that if you needed to. So you do need to be comfortable doing both. But hopefully this question wasn't too bad. Hopefully we all kind of remember this from last year anyway.